Good evening, everyone. I'm Calvin Joseph, and today we'll be conducting the week 11 problem solving and doubt clearing session for the course Electrical Measurements and Electronic Instrumentation, which was taught by Professor Abhishek Chatterjee of IIT Kharagpur. So the outline of what I'm going to teach today is how we can use integrator, how we can make an integrator using op-amps, how we can build our own function generator circuit, and what is a 555 timer circuit, and what is a stable oscillator circuit, what about a monostable oscillator circuit. And then we will learn a little bit of what oscilloscopes are, and then we will solve some few example sums and some LTSpice simulations. Okay. So I'll start with what we have to do today. Today we are going to focus on week 11. So one circuit which we have to use is an integrator circuit. An integrator. So you all have learned maths, okay? And you have learned calculus, you have learned integration, you have learned differentiation, etc. So now what if we want to do some integration of something using some circuits? Using an electronic circuit, we want to do certain integration. So how can we do that? There is a circuit which is known as an integrator, which is built using op-amps. So let us say this is by op-amp. Okay, this is a minus terminal, positive terminal. This is a plus V supply. This is minus V supply. This is the output of the integrator. The integrator works in negative feedback. So there is a capacitor is present. Through a capacitor, we feed the output signal back to negative terminal. And over here, we have a resistor. So this is the R, this C. This is my input. And this is connected to my ground. Okay. So if we want to analyze this circuit, we can, R can be written as R. Capacitor can be written as 1 upon SC. Okay. So by virtual ground concept, what is the current which is flowing? No current can flow into the op-amp. Okay, so the current which is flowing like this should flow out like this. And this potential is at what potential? It is at zero potential, right? Because this is connected to ground, and because of virtual ground concept, this also is connected to zero. So the current I is V in upon R. And this current I is going over here, right? So this point is zero, so 0 minus the output upon the capacitance, so 1 upon SC is equal to your I. So we can equate it as minus the output by of S into S into C is equal to I, which is V in upon R. So your V output of S is equal to minus V in of S upon S RC. Okay, so we know, so this actually is minus 1 upon RC into 1 upon S into V in upon S. This S is the Laplace domain operator. And in Laplace domain, how do we represent an integrator? Does anyone know?
One by A.
Yes. So this is actually your integrator term. So if we write in time domain, my V output of T, okay, is actually minus 1 upon RC integration of V in of T into dt plus V output at time T0, okay, at the initial time T0. And this is going from T0 to time T, okay. So what is this known as the initial condition? The initial condition of the integrator. Okay, so the initial condition of the integrator also we must know, and that will happen in the circuit. Okay, that depends on what is the voltage in the capacitor, etc. All that will happen. So the output voltage at a particular time depends on the initial condition as well as this slope and what voltage is applied over here. Okay, so effectively we are integrating the input voltage and we are getting the output voltage. So what will happen if assume my V output T0 is equal to 0. Okay, and my V in of T is equal to A into sine T. Assume it is A into sine T. So what will be my V output of T in such a case? What is V out of T? So what we have to do? We have to substitute. So V out of T, and let us assume T0 is equal to 0. This is minus 1 upon RC, integration from 0 to T, A into sine T into dt plus 0. So the V output of T minus 1 upon RC into A. What is integration of sine T?
Minus cos T.
So it is minus cos T plus 0. So V output of T actually A upon RC into cos T. Okay. A better example I see rather than it would be A sin omega T. So this is A sin omega T. Because A sin omega T is sin of omega T using minus cos omega T and omega will come the denominator. Okay. So be A omega RC cos of omega T. Okay. So if I apply a sine input, then my output also will be an integration of the sine. So output will become cosine. If I apply a cosine, then my output will be a sine wave. So is this part clear?
ये फर्स्ट वाला स्टेप बता दीजिए तो थोड़ा सा रिपीट कर दीजिए
जो ये वाला
ना 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 जस्ट नीचे से नीचे एक स्लाइड हाँ ये V out
ये
T
part
equal to हाँ हाँ ये सब थोड़ा सा
अच्छा इंटीग्रेशन ये 1/s मतलब इंटीग्रेटर है ठीक है RC जो है RC is a constant so RC can be taken out so this 1/s is representative in time domain it is terms of T0 to T. Okay, so that means let me go down. Suppose you have 1/s into something, let us say x of s or something. So this in the inverse Laplace transform of this will be equal to some T0 to T x of t into dt. Okay, so ये लाप्लास है ये इनवर्स लाप्लास है तो वही मैं यहाँ पे लिख दिया ठीक है तो
लास्ट वाला स्टेप है सर उसमें लास्ट जो है उसके बाद जो है
ये वाला
इंटीग्रेशन के बाद
यहाँ
नो
पे
नो सर उसी में सर V out into T0 की है उसी में सर उसी स्टेप में
अच्छा वी आउट T0 अच्छा वो
ये
अच्छा ये इनिशियल कंडीशन है जो पहले जो एक वैल्यू जो था ना वो ये मैं कैसा समझाऊँ मतलब आप कुछ वैल्यू इंटीग्रेशन मतलब क्या, आप ऐड कर रहे हो ना, आप ऐड कर रहे हैं प्रीवियस वैल्यू के साथ, तो वो प्रीवियस वैल्यू रहना चाहिए, वो है इनिशियल कंडीशन।
इनिशियल और फाइनल कंडीशन हो रहा है क्या सर?
हाँ हाँ, नहीं नहीं, ये इनिशियल कंडीशन है। जो डिफरेंशियल इक्वेशन जब भी आप सॉल्व करते हो तो आपको फाइनली ये इंटीग्रेट करते हो वो डिफरेंशियल इक्वेशन को, उसके बाद आपको एक कांस्टेंट ऑफ इंटीग्रेशन आता है ना, और वो कांस्टेंट ऑफ इंटीग्रेशन का वैल्यू आप
यस
कैसे
सर।
ढूंढते हैं, इनिशियल कंडीशन डाल, तो यही है वो इनिशियल कंडीशन जो कांस्टेंट ऑफ इंटीग्रेशन हो जाती है।
ओके सर, थैंक यू सर।
ठीक है, तो if I if I apply sine wave, I'm getting a cosine wave. Now, what if my input is some plus 10? Okay, so my V output of t is equal to minus 1 by RC t0 to t into V in of t into dt plus V out the previous initial condition. So that is equal to minus 1 by RC t0 to t 10. 10 is a constant, so it is 10 into dt plus V output into T0. So this is equal to minus 10 upon RC integration from T0 to T dt plus V out of T0, right? So it is minus 10 upon RC T from T0 to T plus V output of T0. So this is equal to minus 10 upon RC T minus T0 plus V output of T0. Okay. So if you plot this, like if you make things easy, to simplify, let us take T0 0, V output of T0 also 0. So V output of T is actually minus 10 upon RC into T. This means this is your time, right? And this is your plus 10. So this is how your input is changing with time. How is your output changing? The output is starting from 0. Let me draw a different color. The output is starting from 0. And it is like moving like this. Okay? And what is the slope? Minus 10 upon RC. Any confusion in this?
No sir.
Okay. So what if I apply, what if instead of minus 10, what if it was, instead of plus 10, if it was minus 10? Then it would increase like this. And the slope would have been 10 upon RC. Okay. So if I apply a DC value to my integrator, the integrator will start to increase its voltage in a linear slope. Okay, it will be a linear slope, it will increase the voltage. So now we will go to the next part, which is known as the function generator. So does anyone remember what is a Schmidt trigger?
It has two state, means a final positive state or final negative state.
Okay, and why do we use Schmidt trigger?
नॉइज हटाने के लिए.
Okay, so what do we have is, we have an integrator is there, and we have what is known as a Schmidt trigger. So what will be the output of my Schmidt trigger? Can anyone tell me what will be the output of the Schmidt trigger? As Sangeeta was
sir.
saying, what will be the
Square
output of
wave.
this square wave? Schmidt trigger can only have two values, plus V supply or minus V supply. That will be either plus V supply, minus V supply, plus V supply, minus V supply. So just like a square wave. Okay. This and it has this is the DC value 0. This is fed as an input to my integrator. So what will be the output of my integrator? When V supply is positive,
Angular wave.
your integrator value is going low. When V supply is negative, it is going high. So it is going low, high. So it is like, so this is, let us say V1, this is V2. So your V1 is a triangular wave. Your V2 is a square wave. So this is the overall functional block diagram. I have a Schmidt trigger, I
सर
have
ये
a
इंटीग्रेटर के बाद ट्रायंगुलर वेव कैसे हुआ इंटीग्रेटर के बाद?
हाँ वो मैं बता रहा हूँ एक मिनट. तो अब आपने देखा यहाँ पे कि मेरा इनपुट जो है यहाँ पे देखो इनपुट है +10. जो इनपुट है वो +10 है. जब भी इनपुट +10 है ना तो आपका इंटीग्रेटर का क्या हो रहा है? इंटीग्रेटर आउटपुट लीनियरली रिड्यूस हो रहा है. हाँ यहाँ पे लीनियरली ऐसा रिड्यूस हो रहा है. ठीक है. पर अगर आपका इनपुट वोल्टेज ये होता -10 तो आपका इंटीग्रेटर का आउटपुट ऐसा लीनियरली बढ़ रहा है. हाँ एक स्लोप के साथ. ठीक है. तो एक है पॉजिटिव एक है नेगेटिव. तो यहाँ पे मेरा आउटपुट क्या है? इधर पॉजिटिव है या नेगेटिव है. तो इधर भी वही वोल्टेज आएगा, इधर पॉजिटिव है या नेगेटिव है. तो जब यहाँ का वोल्टेज मान लो पॉजिटिव है, जब यहाँ का वोल्टेज पॉजिटिव है तब आपका इंटीग्रेटर क्या करेगा? उसका जो भी वोल्टेज रहेगा वो गिरते जाएगा. जब आपका इंटीग्रेटर का इनपुट नेगेटिव हो जाएगा तो इसका क्या होगा? वो लिनियरली बढ़ता जाएगा. जब ये वापस पॉजिटिव हो जाएगा तो ये वापस गिरते जाएगा और जब ये नेगेटिव होगा ये वापस बढ़ते जाएगा. तो ये हो गया इंटीग्रेटर. ये है
ओके सर.
इंटीग्रेटर का काम. ठीक है. So this is how it works. This is the logic. This is just simple for you to understand how you actually make an integrator circuit. It will look like this. Okay. You can have your integrator. Then you have your capacitor C. Right. This is the output of the integrator. And then you have your Schmidt trigger. Negative, ground. This is your R2, this is your R1. This is your V1, this is your V2, and this is again connected over here. Okay. So this part is your integrator. And this part is your Schmidt trigger. Okay. Any doubts in this circuit?
No, sir.
So the Schmidt trigger, is it a inverting or non-inverting Schmidt trigger?
Non-inverting, sir.
Yeah. So this is a non-inverting Schmidt trigger. Okay. So what happens is Mm, so this is real line. Okay. Assume your Schmidt-Trigger's output was positive. Was positive. Okay. And your integrator was at some voltage. And because it is positive, it is reducing. It reaches some value. Some value it reaches. Now it reaches, let us say, suppose there's some voltage over here, and there's some voltage over here. Okay. This is known as your lower trigger point. This is known as your upper trigger point. Hmm? So this has reached this low value. Okay, it has reached this low value over here. It has reached this value over here. Then what will happen to your Schmidt trigger? Your Schmidt trigger will get triggered. So in this positive value, it will go to the negative value. And it will remain like this. Then what will happen to your integrator? Your integrator will increase. It will reach this value. That time what will happen to your Schmidt trigger? Once it reaches the upper trigger point, it will go positive. So then this will start reducing. Okay. So this is your V2, this is your V1. Right? Any doubts?
No, sir.
So we will also do some simulations of the LTSpice. So you can see this actually happen. So you must understand that in this bounded, this wave is bounded between the upper trigger point and the lower trigger point. Okay. And it will have some time period. This is your T1 and this is your T2. Okay. So you must, so you are going from here to here. So this is a straight line, right? And that slope is given by V supply by RC. And then minus V supply by RC is the slope over here. So using this, you can find out what is the frequency. So your time period will be just T, and your frequency is 1 by T. And this band, your triangular wave will have amplitude. What will be the amplitude of your triangular wave? Will be upper trigger point minus lower trigger. Or your amplitude actually is your upper trigger because it is symmetrical around zero. And what is the amplitude of this? It is your plus V supply. Is the amplitude uh, of your Schmidt trigger. Okay. Okay, so now we have to go for the 555 timer. So we have to look at the 555 nano circuit. So before we look at that, we must understand one thing. If instead of an integrator, we had a RC circuit. Okay, you have a resistor, you have a capacitor, this connected to your ground. And over here, what do you have? You have a pulse. It is either plus V supply or minus V supply. Right? So what is the voltage over here, please? Suppose now this is your input, okay? This is your input. This is your output. Suppose your Vin is equal to V supply. So how will your VC voltage change? Your VC voltage, let us say it was at some value. The VC voltage will start increasing. And how do you express that? You must understand that when I've applied a positive voltage here, at steady state, we want the voltage, that same voltage will come across the capacitor. We'll charge the capacitor to that voltage. Okay, at steady state. So your target voltage is V supply. And your initial voltage is some value. Let us say your initial voltage is some V initial. VC initial. Okay. So your VC of T will be equal to your target voltage plus initial minus target upon e raised to minus T upon tau. Where your tau is equal to R into C. So that's the time constant of your circuit. So now, how do we verify this equation? When T is equal to 0, what will be e to the power minus T by tau?
1, sir.
Will be 1. So what is your VC of 0 then?
It's initial value, sir.
Will be initial. Right? At T equal to infinity, what is your e to the power minus T by tau?
Zero.
Target heading, sir. Target heading, you know, sir.
No. So e to the power minus T by tau is 0.
Zero होगा ना?
हाँ सही 0 होगा तो आपका VC of infinity क्या होगा? Target होगा. Okay. So this is how we know that this equation is correct. So that final like maximum infinity value, this should be equal to target, and at 0 it is your initial. So this equation is correct. Okay, so this is how this equation is a very useful equation which we will use a lot in the upcoming 555 timer circuit. Okay. So let us say we have a resistor here, another resistor here, another resistor here, which is connected to your ground. Okay. Next, I have a set of op-amps. Okay. This is connected here. This is connected here. And these two are connected to some voltage, let us say Vx. This is your V supply. Okay. What will be the current going in over here? Huh? What is the current entering the opener? What should it ideally be?
0, sir.
Yeah,
Zero होगा.
हाँ सही. तो वो current 0 होना चाहिए. So what will be the voltage over here then? this resistor, this resistor, this resistor, all are of equal resistance value. So what will be the
ये सर
voltage over
भी
here?
सप्लाई का 1/3 होगा.
Here, the voltage will be V supply by 3. Over here, what will be the voltage?
2/3 होगा सर.
Over here, the voltage will be 2/3 V supply. Okay. Now, what will this be? If your Vx is greater than 2/3 V supply, then this is positive. If your Vx is less than 2/3 V supply, it is negative. So this can take value 1 or 0, 1 or 0, any of them. So if your Vx, this happens when your Vx is greater
Sir,
than 2 by 3 V.
repeat once again sir please.
हाँ,
ये जो
ये है आपका Vx ना, Vx आपका इधर आ रहा है. जब भी आपका Vx is greater than 2 by 3 V supply, तो आपका ओपन का आउटपुट 1 होगा, to be 1.
right sir.
And if your Vx is less than 2 by 3 V output, then your open's output is 0 or minus.
Okay.
It is either high
Okay.
or low. Okay, let us work in digital terms. It is either high or low. Now, for this op-amp, Vx is coming to a positive terminal. So this is 1 when your Vx is greater than 1 by 3 V. Okay, when your Vx is greater than 1/3 of your V supply. Sorry, this should be your V supply. When your Vx is greater than 1 by 3 V supply, it is 1, and it is 0 when your Vx is less than 1 by 3 V supply. Okay. So this is your VA, this is your VB. We found what is VA and what is VB. So now we need to have a logic. And what our logic says is, this suppose is your set reset flip flop, and this is your NOT gate. Okay, this is your NOT gate. So this is my VA, this is my VB, and this is the Q. So if my VA is 1, that is because my Vx is greater than 2 by 3 V supply. Then what will be the set value? The set value will be 0. But if my VA is 0, then the set value will be 1. Then if my V is 1, then the reset value is 0, and if VB is 0, the reset value is 1. So what logic I actually want to do is, I want it to give either a positive or negative value. Okay. So this is my Q. Okay, this is my Q. So till here, is it clear? how we are getting Q using the SR flip-flop?
Yes, sir.
Okay. So that means, so now this Q which is there will go. So there will be another circuit over here. Here your R and this your C. Okay. This is C, this is your R, let us say Rx. And this will come over here. Q will come over here. Okay. What's it? What's the mistake? Space. There's this your RF, this is your R, right? This is V supply. And this is BJT and Q comes over here. Q comes over here. So when Q is 1, what will happen over here? If your Q, okay, let us consider first thing. If the Q is 0, my Q is 0. If my Q is 0, what will happen is this will charge. Okay. Your current will flow like this, and your capacitor will charge. Its voltage will keep on increasing. Right? Now, if your Q was 1, then what will happen? This is turned on. So it will discharge like this. It will discharge like this. Okay. Your capacitor will discharge like this. So if Q is 0, your capacitor voltage will increase. That means your VC will increase. And if your Q is 1, that means your VC will reduce. Is this clear? So if your Q is 0 means what? Your BJT is turned on, turned off. So that means your capacitor is getting charged through RY and RH. And if your Q is 1, that means your capacitor is getting discharged through RH. It will get discharged. Okay. And this voltage Vx is actually used for triggering these op-amps. Okay. So let me draw the diagram. So let us say this is my VC. Okay. This is my V supply by 3. This is my 2 by 3 V supply. Okay. So let us say the voltage was somewhere over here. This is your VC. Okay. Your voltage across your capacitor was somewhere over here. And what is your state of Q time? This is Q. So Q was high. If Q is on, that means what? Your voltage over here will reduce. It will reduce. And then it will touch this point. When it touches this point, what will happen? Your Q will become 0. When Q becomes 0, it will charge like this. And when it reaches this point, what will happen? Your Q0 will become 1. Okay. So that means your Q has become 1. Again, it should discharge. So it will discharge like this. Okay. It will discharge like this. Then it again reaches this point. Then what will happen? Your Q will again become like 0. When Q again becomes less than 0, it will again start charging. Okay. So this is how it goes. So it has a time. This is your T1. This is your T3. So this is how it is generating a pulse. It is generating a pulse of the entire time period t, and this is the time t2 is when your pulse is on, and this is the time t1 when your pulse is off. And in this case, when it is charging, your tau is equal to Rx into C. It is actually equal to Rx plus Ry into C when your tau is off. Right? When your tau is off, when this is 0, that means it is charging. So it is Rx plus Ry into C. So this is your tau off. And the tau on over here will be equal to Rx into C. Because only this resistor and this capacitor is coming to the picture. Okay. Is this part clear about the 555 timer works?
Yes, sir.
Okay. So to improve, actually, let me show this machine. Let's can understand. First, let me show this. So, can you see the circuit, right? So this is some V1. Okay. First of all, this is your plus V. Your plus V means over here I have said plus V as 9 volt. So that means 9 volt is over here. Then there are equal resistances of 5K, 5K, and 5K. So what will be the voltage over here? At this point,
1/3 of V plus.
1/3 of plus V, and plus V is 9, so this will be 3 volt, this will be 6 volt. Okay. And this is some sort of time varying signal. This is signal which varies with time. I just given it initially, so you can understand this part of your 555 time. So let me run it. So at this point, what should be the voltage? It will be around 6 volt. There's again small oscillations, but that is minimal. Over here, the voltage will be 3 volt. Okay, so the voltage over here is 3 volt. The voltage over here is 6 volt. What is this voltage applied over here? This is just a sine wave input out here. And the 555 timer circuit, which I have shown, there's no sine wave, but this is just to test the logic. So what is happening when this goes above this value? What is happening here? When this goes above this value, this is turning red. And when this goes below this value, this is turning red. Okay, again, when it is going above this value, it is turning red. When it is going below this value, it is turning red. So this is similar to the operation of that capacitor timer. But then this red voltage, which is over here, will change. Okay. So this part, any confusion, any doubts?
No, sir.
So, it's something. Okay, 2.8. I have given the DC offset 4.5. What 2.8? DC offset is 4.5. I have wantedly given it. Now, let me go to the actual voltage circuit. Over here. Okay. So first, First, I will look at the voltage over here. It's around 3 volts. The voltage here is around 6 volts. So this is the upper trigger point and lower trigger point, kind of similar to that concept. Okay. And then this is a voltage across the capacitor. So when it hits over here, what happens over here? This goes low. It goes low. So what is actually happening? Can you let me try to explain it. Better way is okay. This is better way. So now what is happening is when this is high, when this is on, when your Q is on, what is happening? Your transistor, NPN transistor is on. So when your NPN transistor is on, what will happen? Your capacitor will discharge like this. Your capacitor current will flow like this and it will discharge over here. So that's why your capacitor voltage is reducing. Okay, so you can see your capacitor voltage is reducing. Then once it reaches this voltage of 3 volt, okay, it has reached this voltage of 3 volt. It is compared over here and here. So when it is reaching, it is going less than 3 volt. What is happening? This is going high. If this is going high, it is resetting your SR flip flop, and so your Q becomes 0. So your Q has become 0. When your Q has become 0, your transistor has turned off. That means no current will flow. So your current then has to flow like this. Your current will flow like this, it will flow, like this it will flow, like this it will flow. Okay, and as it will flow like this, what will happen? Your voltage across your capacitor will rise. It will rise and reach that 6. When it reaches 6 volt, what happens is this becomes more than 6 volt. So this will become 1. When this becomes 1 means set is 1. When set is 1 means what? Your Q becomes 1. So your Q has become 1. When your Q has become 1, what will happen now? Your transistor will turn on. So then the current will flow out like this. It will flow out of your capacitor, discharge the capacitor through this way. Okay, so this is how your 555 timer circuit works. Any doubts in this?
No, sir.
Okay. So, this is the working of your 555 timer. And now we will go to the next topic. So your constants, your time constants also will change, and your time also will depend on your time constants. Okay, so from that we can make some derivations of what will be the frequency, etc. And we have some sums. When we solve that, we will understand those constants even better. So now we have a stable oscillator circuit. So this astable oscillator circuit is a circuit whose output will not remain fixed. Its output will keep on changing. It will go high, low, high, low, high, low, etc. It keeps on varying. And how is it made is this we have one inverting symmetry. Okay. So this is an RA, this is an RP. This is the inverting part of the symmetry. It is your input voltage applicable. This out, and then there's a resistor here, there's a capacitor here, and this is coming over here. Okay. This is going here. This is the output. It has been fed here. This is your R. This is so this part. This part is your inverting mid-range. Okay. And this part is similar to your integrator, or kind of like an integrator. It is similar to an integrator. Except it is not exactly a proper integrator, pure integrator. It has some certain exponential rise, exponential fall, but it is similar to an integrator. Okay. So now, what happens is, if this V output is, let us say, plus V supply. Okay, it's plus V supply. Then what will happen over here? Your capacitor voltage will start rising. It will reach the upper trigger point, and then this will output will become minus V supply. Then when minus V supply happens, what will happen? Your capacitor voltage will reduce. Then it will reach a lower trigger point and again will come. So let me draw the waveform, because I think waveforms are the best way for you to understand it. So let us say, so my output is at some value. Okay, like my V output is at plus V supply. Okay, there is the upper trigger point, there is the lower trigger point. Okay, now output is at plus V supply. So what will happen is this will rise, and once it reaches the maximum value, upper trigger point, what will happen? This will go negative. It will be fixed at minus V supply. Okay, it goes to minus V supply. So then what happens over here? It will start discharging. It will reach a lower trigger point. Then what will happen? This will again go high. Then this will what will happen? This will again go high. Then when it reaches that point, this will go low. And this will again go low. Okay, so your output is changing from one state to another state, again back to this state, then again back to this state. So it is keeping on changing continuously. It doesn't have a fixed value. It is oscillating from one state to another state, next state, back to that state, again. So it is going to be like unstable. That is why it is known as an astable oscillator. Right. Any doubts in this?
No, sir.
So, this is there. Astable oscillator circuit is also present. So, this is my inverting Schmidt trigger. Okay. And these are certain resistors which I have given. Some resistors on them. And this is my RC circuit. Okay. This is the same circuit which we have made. So let me run it. So we run it. So my output is either positive or negative. And this is my capacitor voltage. Let me change the time. Okay, then it looks better. So now, when my output is high, okay, then what is happening is my capacitor is getting charged. It is rising. Once it reaches the upper trigger point, what happens is the inversion trigger goes negative. Then this also starts reducing. Then when it reaches again the upper trigger point, means a lower trigger, when it reaches the lower trigger point, then it becomes positive. So then it again starts rising. Okay. So in this way, what is your output? Your output is this green curve, okay, your green signal. So it is keeping on changing. This is the one value or next value, again back to the same value. So it is kind of like known as a stable or unstable oscillator. So this is also useful. What are we effectively generating? We are generating a square wave, kind of like a square wave, like using a inverting symmetry. Now, how do you change the frequency of the wave or the signal? Can you change the frequency? Is there any way I can change the frequency? Yeah, I see. I can see. So what I will do is, yes. It will spice that. And this 1K which is here, right? I will modify it to be a variable R. Okay, it's just a variable R. And the R is changing from 1K to 5K in steps of 1K. So there'll be first will be 1K, it will run the simulation, then it'll make it 2K, it will run the simulation, make it 3K, run the simulation, 4K, run it, and 5K it will run. All those things it will show. Let us see how it looks. So it is actually not understandable so much currently. Not that clear. It was not that so. Okay. So in one case, with 1K, my frequency is so high. Okay, my frequency. It is like changing so fast. It is changing it so fast. But when I make the resistor 10K, it is changing at the blue curve, at the frequency of the blue curve. And when I made a resistor 100K, means that time constant has become very large, its frequency has become so small. Like it is taking so much more time. It is the red curve. Okay. So this is how, when you change your R value, you can change the frequency of your signal. Any queries in this?
No, sir.
So all these things are there. So you guys also can use LTSpice to check, to verify, like to believe that what sir is showing, what sir is teaching actually truly happens. Okay. So this is simulation. Later on, if you have the provision, you can also, use a breadboard, you can use the op amp, you can use the capacitor, resistor, etc. And you can actually run all these things and actually see them. Okay. So these are interesting things for you to explore. So these are stable multi-vibrator. So now what is done is with this circuit is this voltage is either V supply or minus V supply. So what they do is in a monostable oscillator circuit, they are like a monostable oscillator circuit. Yeah, negative here, positive here. This is here. This is connected to the ground. This is connected to your R, C, ground, and this C comes over here. This is your first stable oscillator circuit. So this has two values, plus V supply, minus V supply. And this is your DC. What they do is they connect a diode over here. Diode is connected. So your BC can go maximum to 0.7 volt. Let us say the diode drop is 0.7 volt. So what happens is your VC can go maximum to 0.7 volt. It cannot go more than 0.7. And if that happens, what will happen? Huh? If this VC can go maximum 0.7 volt, then what does it mean? Yeah, it will not reach the upper trigger point, so it will stay positive. Okay, it will not become zero. So that is why it will always be V supply plus V supply, so we keep on charging. And by any means, by some problem or the other, or by some issue, if this output is minus V supply, let us say it is minus V supply, by some noise or something, it is minus V supply. And then what will happen? Your capacitor will start reducing. The voltage of your capacitor will start reducing, and at some case it will become less than the lower trigger point. So then what will happen is my trigger will become positive. So by default, this voltage is always positive. It is stable. Stable at plus V supply. It is stable at plus V supply. Now what they do is, at this point, they use a switch and they connect it to some minus VT. Okay, they connect it to some minus VT. So what does this do? Sorry, it is not connected there. It is connected over here. It's connected over here. So this is either connected to your this, or it is either connected to your ground. Two options. Okay, there are two options. It can either be connected to your ground or it could be either connected to minus. So when it is only connected to ground, the output is plus V supply. And when it gets connected to minus VT, for a small moment, your output will become minus V supply. And then from minus VT, we again connected to ground, the output will again become plus V supply. Okay. So this is how a monostable oscillator circuit will work. It is always stable at plus V supply, but if we connect it to minus VT for some time, then your output, so your VT, let us say, your output is positive only. At some time, I give this small VT pulse. Then this will be negative for some time, and then again it becomes positive. Then again I give some pulse. It will again go negative for some time, then it will again become positive. So for a short, small duration, it goes from the stable position to the unstable position. And then again it goes back to the stable position. So when the small pulse comes again, it goes low. And it be slow for some time. Then it goes high. Okay. So what is happening is this is actually acting as your trigger. This is actually acting as your trigger. And it will stay in that unstable position for some duration. For this duration, it will stay in that unstable position. So inherently, the circuit in by default state is stable. But when we trigger it, okay, when we trigger it using a negative pulse, then it goes zero for some time, and then that is it's kind of like a fixed time, and then it again becomes stable. Okay. So any doubts in this? Okay. So then we come to oscilloscopes. Now let's go to oscilloscopes. Acha, so you guys all attended sir's Abhishek sir's session today at 3 p.m. You guys attended or didn't attend? Oh, okay. No. So even I got a message, so but I was busy, I couldn't get it. But I guess probably it would be recorded somewhere, so you can also check it. So Abhishek sir teaches a lot of stuff in this course, and Abhishek sir actually takes a lot of pain, and he's demonstrating the concept. He's showing how in the oscilloscope how the waveform will work. All that. So that's very rare. That's also a very good way of teaching. So, and I guess you have cleared your doubts probably if you have joined. Yeah. So now we will consider something very important thing which I am understanding the importance of it. So that is known as your oscilloscope. So we did all these simulations. Okay, let us again open this and stay in oscilloscope. Go back to, So I ran this circuit. Okay. Now I connect this signal and I connect this and I'm able to see this. So in the real life, in actual real life, what we will do is we will use a breadboard and we will make this entire circuit connection. We will use resistor, capacitor. We'll have to use a voltage source and give plus 12 volt, minus 12 volt, use a op amp, etc. We have to make this entire arrangement. Okay, so we can see the op amp, we can see the resistor, we can see the capacitor, all that we can see. But now, how do we see the voltage? One is like we may say we can connect a voltmeter. So if I connect a voltmeter, what will it tell me? If I connect my voltmeter to this point over here, okay, to this point over here, V2, what will the voltmeter show me? The voltmeter, it will show me 0 volt. The voltmeter which I connect, it will show me 0 volt. So then what will I think is my circuit is not working. But actually 0 volt is not coming. There is some voltage which is coming. The average voltage which is coming at this point is 0 volt. If you see over here, if you see the average value is 0. Okay, the average value over here is 0. Now, the average value of my signal is 0 volt. Okay, it is 0 volt. So my voltmeter will show me 0 volt, but the actual signal is not 0 volt. Okay, we must understand the actual signal is oscillatory signal, the DC value is 0. So now how can I see this circuit in real life? So for that, I will need an oscilloscope. So there will be an instrument which is known as an oscilloscope, in which I will connect one probe terminal here and another probe terminal I connect here. So I connect the probe terminal over here with respect to the ground. And then I will see the signal with respect to the ground. And that signal will look like this. Then if I connect this one more probe over here, I will see my voltage. I will see how the voltage across the capacitor is looking. So these signals, if I actually want to see it in real life, if I want to see these signals in real life, I need to use an oscilloscope. So the oscilloscope will display how the signal is looking. Okay, the oscilloscope will display how the signal is looking on the screen. And then I can understand if my circuit is working or not working. So this is the simple basic understanding of an oscilloscope. We know voltmeter will measure the voltage, but it will either show you the RMS value or it will show the DC value. But it will not show you how the signal is changing with time. It will not show you how the signal is changing with time. If I just connect a voltmeter here to this capacitor voltage, it will show me 0 volt. If it is measuring DC. If it is measuring RMS, it will say suppose some 3 volt or 4 volt, it will show. But I want to see how the voltage across the capacitor, I want to see the voltage charging, I want to see the discharging. All that if I want to see with my eyes, I will need an oscilloscope. So that is what an oscilloscope is used for. So the oscilloscopes are two types. One is your CRT, that is your cathode ray tube. Okay. So in that, there is a horizontal voltage which is applied and a vertical voltage which is applied. Okay. So this is what sets your time base, and this is your actual signal. So this is your time. Your time will go like this. And your signal is like what? Your capacitor, which is charging, discharging, charging, discharging. So this is like your time for your entire screen. So like say this from 0 to 10. So it will show from 0 to 10 seconds, something will show. Then for 10.1 second to 20 second, it will again show the new screen. It will again show the same screen. Okay. So that's how your cathode ray tube works. Nowadays, CRTs are not that useful because it is always instantaneous. It cannot, store data and then show it. It cannot do like many measurements, etc. It is limited. So cathode ray tube is very like olden times. Okay, it's olden times. So basically, how it works is it will deflection of electron. Okay, deflection of the electron using the fields. Two fields are generated by this VH of T and VB of T. Okay, these voltages, they will deflect your electron beam, and that deflection you will see on your oscilloscope, on your cathode ray tube. Next is your DSO. Okay, next is your DSO. Your DSO is your digital storage oscilloscope. So in my lab, we use this, and DSOs are like quite expensive. It depends. If you're using very high-end one, it will be very costly. Simple one can also be used, and that you can buy. So this DSO has the ability to store. It can, store the signals. It can store the signals. It can also do measurements. It can do calculations. It can do the fast Fourier transform, etc. All these things your DSO can do. Okay. It can also measure the frequency of your signal. It can measure the time period of your signal, right? You guys studied, na? We used something known as a digital frequency meter. That all those concepts which we studied, all that, all these electronic, calculations, etc. DSOs have. Okay, not all DSOs will have everything, but most DSOs will have a good, reasonable amount of mathematics. It can do. It can do some calculations. It can show RMS value. It can show the mean value. It can show the DC value of your signal. It can show. Okay, so this is something is there in your DSO. But you must understand one thing. Suppose this is your signal. Okay, this is your signal. It will what it will do. It will capture one point over here, another point over here, another point over here, another point over here, here. The signal it will show something like this. It could show a signal something like this. Okay, but this is not your actual signal. So it will what it will do? It will smoothen it out. It will not sort of smoothen it out on its own. It will like sort of smoothen it out. So your signal will no longer look this square wave thing. It will look similar to this yellow line. But if you want your signal to be very accurate, then what you must do, you must take samples very, very close by. You remember ADC, right? ADC, that is taking samples, right? You take discrete values. So now your signal will be very close because it is taking these small values. So it will show you very accurately. Okay. So there is something known as your sampling frequency in your oscilloscope, which you have to set. So higher sampling frequency, the better. If my sampling frequency is higher, it is good because it will show my signal as accurate as possible. That is the advantage. So now we will, is there any doubts in this part? Okay. So if there are no doubts, I will start the problem solving session. Okay, that we will solve some sums. Okay. So now this is a simple function generator circuit. I have also simulated this. The simulation which I showed, I will also show the simulation for this, and then we will see how accurate is our calculations with the simulations. Okay. So we have this one. Okay, this is my question. So this is my question. So now this part is my integrator. This part is my Schmidt trigger, the non-inverting Schmidt trigger. Okay. So what will be the signal at V2? How will that signal look like? Can anyone tell me?
Square.
The signal at V2 will be a square wave. This is a signal at V2. What will be the signal at V1?
Triangular.
Triangular.
So it will be a triangular wave going like this, like this, like this. Okay, this is your V1. Now, when this is high, this is plus, it is plus 12 volt. And now when it is low, it is minus 12. Here will be minus 12 volt, here will be plus 12. Right? Okay. Now, your V1 is this triangular wave. Okay. My drawing is not very good. That's why I like to show simulations so that you can understand better. But what I want you to see is when this is plus 12 volt, it has started from some value. Okay, that is known as your upper trigger point. and it reaches a lower value, that is known as a lower trigger point. Okay. So for your non-inverting Schmidt trigger, what is the formula for your upper trigger point? Does anyone know?
R2 1 plus R2 by
Sorry? So you're saying
sir,
something?
1 plus R2 by R1.
No, not 1 plus R2 by R1. Your upper trigger point actually is given by V supply into R3, no, into R2 by R2 plus R3. Okay, that is known as your upper trigger point. Okay, let us derive it. Better way is we derive it. So suppose your V2 output was actually plus V supply. That is this plus 12 volt. It should go to some voltage such that it will become minus V12. So this should reduce, right? So this V3 should be less than 0 volt. Now what is your VP? This voltage over here VP is actually this V supply into R2 plus this V1 into R. So this actually is the VP is V supply into R2 plus V in into R3 by R2 plus R, right?
Yes, sir.
So now your VP should become less than 0 volt, right? That means your V supply into R2 plus V in into R3 should be less than 0. That means your V supply into R2 minus V supply into R2, let us leave this, less than minus V in into R3. So minus V supply into R2 should be greater than V in into R3. So minus V supply into R2 by R3 is greater than V in. So when your V in becomes less than minus V supply into R2 by R3, then it changes. So this is known as your lower trigger point. When your V in goes less than minus V supply into R2 by R3, that is this value, then it changes. Okay. Any queries?
नहीं सर और एक बार समझा दीजिए.
तो पहला आपका ये आउटपुट मान लो प्लस 12 वोल्ट, ठीक है. अभी वो क्या कहता है, ये गिरता जाएगा, तो किस वोल्टेज पे ये मेरा माइनस 12 वोल्ट हो जाएगा, वो मेरे को देखना. तो ये कभी होगा जब ये जो वीपी वोल्टेज जो रहेगा ना वो 0 से कम होगा. जब आपका वीपी इज लेस देन आपका वीएन, मतलब आपका वीपी इज लेस देन 0, फिर आपका ये वोल्टेज वो नेगेटिव चला जाएगा. हाँ, तो उसके लिए क्या करना पड़ता है, वीपी हमारा लेस देन 0 रहना चाहिए. आपका वीपी का फॉर्मूला इस तरह दिया जाता है, V supply into R2 plus V in into R3 by R2 plus R3 to be less than 0. So V supply into R2 plus V in into R3 is less than 0. So that means your V supply into R3 is less than minus V in R3. और ये सब मैथ करने के बाद आपका इनपुट वोल्टेज अगर लेस देन माइनस V supply into R2 by R3 हो गया तो आपका स्टेट चेंज हो जाएगा. ठीक है.
ठीक है.
तो उन्होंने क्वेश्चन में क्या पूछा है कि the waveform of V1 is what? Is it sinusoidal, square or triangle? यहाँ पे V1 क्या है, आपका ट्रायंगुलर वेवफॉर्म है. और V2 पे क्या है आपका स्क्वायर वेवफॉर्म, ठीक है। फिर एस्टिमेट द पीक टू पीक एम्पलीट्यूड ऑफ V1। तो इसका पीक टू पीक वैल्यू क्या है? पीक टू पीक आपका रहेगा अपर ट्रिगर पॉइंट माइनस लोअर ट्रिगर पॉइंट। तो आपका पीक टू पीक is upper trigger point minus lower trigger point. It is V supply into R2 by R3 minus of minus V supply into R2 by R3. So this is 2 into V supply into R2 by R3. So this is 2 into V supply is 12. R2 is how much? R2 is 3, R3 is 5. 2 into 3 by 5. So how much is this?
$14.4.
14.4. Okay, so it is 14.4 volt. Any queries in this? Okay. So it is 14.4 volt. What is the peak to peak of V2? What is the peak to peak of V2? Peak to peak is what? V max minus V minimum. That is 12 minus 12. So it is 24 volt. It is peak to peak. No? Maximum minus minimum. So 12
Okay, sir.
minus or minus 12. So it is 12 plus 12. So it is 24 volt. Okay.
Okay, sir.
Now, this
सर
is
किसका V1 का?
V2 का V2
हाँ वही ना, V2
maximum
का
value.
स्क्वायर है वो तो।
हाँ, तो स्क्वायर है ना, तो इसलिए -12 से +12 जा रहे हैं, तो उसका पीक टू पीक वैल्यू है +12 माइनस ऑफ -12। तो उसका है पीक टू पीक ऑफ V1 is what? Maximum minus minimum. Maximum is 12, minimum is -12. So it is 12 plus 12. So it is 24 volt. Okay.
Yes, sir.
Now we want to find how much time this is taking. How much is this time T1? And this will be of time T2. Since this is symmetrical, T1 is equal to T2. Okay. So if we find the time T2, we know what is T1. This is increasing at a rate of 12 upon RC. This is the slope. Your V supply by your integrating factor. So V supply by RC. So this is the lower trigger point, this is the upper trigger point, and this is the slope. So we need to find the time. So we know your slope. Your slope is the upper trigger point minus lower trigger point upon the time T. Okay, let us say T2. Your slope we know it is 12 by RC. Upper trigger point minus lower trigger point is what? Is your peak to peak of, this is your peak to peak of V2 by T2. So your T2 is actually equal to 14.4 upon 12 into your R into C. So it is equal to 14.4 upon 12 into R. What is your R? Your R is 2K, your C is 500 microfarad. Okay. So it is into 2 into 10 to the power 3 into 500 into 10 to the power minus 6. So your T2 actually is 14.4 upon 12 into 2 into 10 to the power 3 into 500 into 10 to the power minus 6. So how much is this?
1.2.
1.2. Okay. So your time period actually is equal to 2 in your time period is equal to T1 plus T2. Since T1 is equal to T2, so it is equal to 2 into T2. So your time period is 2.4 seconds. Okay. So now, let me open the function generator circuit. So this is your circuit. So this circuit, which was there in your sum, I have made it. Okay, 5K, 3K, 500 micro, 2K, etc. Okay. So this circuit I have made. So now let me simulate. See, this is my. This wave, how will it look? What will be the wave at output at V2? How will the output of V2 look like?
Square.
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 Square. Right? How will the output look at V1?
Triangular.
This triangle. Right? So what we have done, we have seen. Now we will check whether it is matching. So what we did is theoretical, we said it is very ideal case. In simulations, it is a little bit non-ideal. When we will go to actually using a breadboard and make the op-amps, etc., it will be more different. It will deviate. So now we will check one thing. You see, okay. What is the maximum value over here? It is not plus 12. Maximum value over here. What's this? This maximum value. This maximum value V1, it is not 12. Okay, it is actually 10.8 volt. It is actually 10.8 volt. No, it's 10.8. Okay, yeah, some not close. Some visualizing we may think it's 11.2, but it is like around 10.8. So we should actually come plus 12, but it is coming 10.8. Why? So what happens is there is some drop. Some drop happens in the op-amp. Okay. So your output will not exactly be plus 12 minus 12, it will be a little less than that. Okay, so that's why in our case it is 10.8. And in the negative side, cursor 2 is here, it is actually minus 10.8. So now what is your peak to peak? Your peak to peak is your vertical, that is equal to minus 21.62. So we got peak to peak should be 24 volt, but when we are using a slightly practical op-amp, not an ideal op-amp, it is deviating. Okay, it is changing to 21.6. So this is for my op-amp. Okay, my output of my Schmidt trigger. Now let us see for my cursor 2. Okay, I'm going for cursor for this blue trace. So let us go to the maximum point. Okay, at the maximum point, what is the voltage? It is 6.4 volt. It is 6.4 volt. And at the and at the minimum point here, it is minus 6.3. Okay, it will be minus 6.3. But when we did our calculations, what we got, it should be 14.4. So our difference here is 12.719. Difference is 12.719, but according to calculations, how much should be the difference? The difference should be 14.4. So there's a slight deviation is there. Okay. There is quite a bit of deviation because we are using a practical op. It is not an ideal op. So any queries in this?
No, sir. Thank you, sir.
Okay, one more thing I want to show you guys is what is the frequency? So this is at the minimum. This is also at the minimum. So this difference between these two curves is known as my time difference is minus 2.4 seconds, 2.406 seconds, which we also got, right? So this is approximately kind of close. Okay. Okay. So this way we are kind of validated. Like what we have done, we have checked in simulation, it is similar, close to. Okay. So now let me go to next question. What will be next question? Okay. So this is the question. So in this question, okay. So this is where 555 timer circuit, which we know, right? So this is how much this voltage over here will be. What will be the voltage over here?
1/3 of 9, sir.
So it will be
3
3
volt.
volt. Here it will be 6 volt. Okay. This is my capacitor. So if you guys remember, when your Q is high, your capacitor will be discharging from 6 volt to 3 volt. This is your Q, this is your VC. When it reaches 3 volt, this will go to low and then it will start charging. And when it reaches 6 volt, it will again go on and then this will start discharging. Okay. So this is how this 555 timer circuit will work. In this case, Q is on. Okay. In Q is on, what is your time constant? Tau on is equal to this. Tau on is actually equal to 2.5 K into 0.25 milli. Right? So how much is that? What would be your tau on?
Zero 0.625.
It is 0.624 seconds. What is your tau off? Tau off is what? 2K plus 2.5K. So 4.5K into 0.25 milli. How much is it?
$1.125.
Okay, this 9.12 seconds. Okay, so now let us consider for this time T1 and this is the time T2. In this case, T1 and T2 are not equal. So T1 is not equal to T2 because your time constants are different. In the case of the integrator, if you remember, there it was a linear slope and the slopes were fixed. But here it is exponential and the time constants are different. So for T1, let us say, for T1, okay, here in this case, the it is an exponential rise or decay, okay, and the time constant for when it is on and when it is off, they are different. So although they are changing from 6 to 3, the time constants are different. So because the time constants are different, so the time T1 to T2 will not be equal. Okay. So let us consider for T1. For T1, my initial voltage was 6 volts. But what is the target voltage? Ideally, it would have to decay to 0 volt. So its target voltage is 0 volt. So your capacitor voltage equation is what? Target plus initial minus target into E raised to minus T by your tau on. Okay. Now, okay, please. Okay. So, these are your bands. Let me just show the simulation so you can understand. So this is the same simulation. So you see, this is it on or off, and this is your VC. So your VC is changing between 3 volt to 6 volt, 3 volt to 6 volt, 3 volt to 6 volt. And if you see the time when this is increasing, this is off. So this time is more, for more time, this is off. And in this time when it is falling, this is on. So this time is less. Okay. And that this is your 3 volt, this is your 6 volt. So it is bounded between 3 volt and 6 volt. Okay. So now, what is the time? The, at VC of T1, okay, VC of T is target. What is target is? The target is 0. Your initial value is 6. This is 0. E to the power minus T by tau 1. But at VC of T1, your voltage is actually, at this point, at VC of T1, your voltage is 3. So you have to substitute this is equal to 3. So 3 is equal to 6 into E to the power minus T1 by tau 1. So your T1, so what happens? This will be half equal to E to the power minus T1 upon tau on. So E to the power of T1 upon tau on is 2. So your T1 is equal to 2 into ln of, sorry, T1 is equal to tau on into ln of 2. Okay, this is your time T1. Similarly, your time T2 is found by tau of into ln of 2. Any? So this we have derived. This also you will get it. This value also you will get. So what is your tau on? Your tau on is equal to 0.625. So what is 0.625 into ln of 2? How much is this value?
सर ये टाउ ऑन कैसे आया 0.65 नहीं समझ में आया।
अच्छा अच्छा अच्छा, जब भी ये ऑन है ना, जब भी ये ऑन है तभी वो यहाँ से डिस्चार्ज हो रहा है, ठीक है। तो तभी वो कौन सा रेजिस्टर यूज कर रहा है, ये रेजिस्टर और ये कैपेसिटर। तो आपका टाइम कांस्टेंट क्या हुआ, ये 2.5 के इंटू ये 0.25 मिली फैरेड, ठीक है।
ओके
और जब हाँ तो आपका वो 0.625 into ln of 2 how much is got, it comes out to be 0.433, sure. Minus 2 into 0.625, yes, it is 0.43. Okay. Now your, what is your tau off? When it is off, when this is off means it is open, so no current will flow, so it has to flow like this. So this 2k plus 2.5k into capacitance, so it is 4.5k into 0.25 milli, so that is 1.12. So your tau off is equal to 1.12 into ln of 2. How much is this?
0.776.
This is 0.776 seconds. So now we will check in our simulation. The simulation which we have done. In this simulation, what is the time? So this is the time from here. And I have one more question. And this is the time over here. So the difference in time, it was earlier here at 1.8 seconds, here it is at 2.68 seconds. So it has taken actually 784.04 seconds. So that is your 0.7 seconds. 0.784. How much did you get by calculation? You got it 0.776 seconds. Okay, so it is close. It's close to what we got. Now, you will consider it is going, this is the final value, and this is the initial value. Sorry. So from here to here, from here to here, the time difference is 436.7875 milliseconds. This one. So that is 0.436 seconds. But how much did we get? We got 0.433 seconds. So it is very close. Okay. So in this way, our simulation results are close to our calculations. So do you guys have any doubts?
No, sir.
Okay. So if there are no other doubts, then I can finally end the session completely. All right. Okay. So then thank you. Thank you for joining everything.
Thank you, sir.
थैंक यू सर।